Hello, class. Okay, here I am helping hopefully with some of the work that is in related rates section of our textbook. So, related rates are a common tricky spot because there's a lot happening, right? There's a lot of moving pieces, literally, and it's really kind of hard to keep track of everything. So I'm going to go ahead and work out example number 3, problem number 3 from our homework. Please take a look at the checkpoint question and the question on the test review, and always, for those, make sure you're checking your answer keys that are on Canvas. You can always, come see me during office hours, all of that stuff. So the challenge of these is that, again, they're all so different. Okay, so just sort of glancing through some of these homework assignments, the questions, there's not very many, but like question number 1 is talking about like a cylindrical tank being filled up, and they give you how like the volume is changing, and then they're asking you how is the height changing, right? Number 2, kind of out of left field a little bit. So the main idea is that all of these functions, we have to take the derivative with respect to time, which we've taken the derivative of like position with respect to time, right? Um, Fine, but these questions are like, that's like when the position is given to you with t as the variable. None of these equations have like t in the equation, and then we need to take the derivative with respect to time. So essentially, all of these equations, when we take the derivative, we always have to remember it needs like a dx dt or a dy dt or a dA dt, whatever the variable is. If it's changing, it needs to have a dA dt with it, or a dx dt, right? It's always with respect to time. So question number 3 is a doozy because there's a lot going on. I'm going to go ahead and I opened up this PDF to sort of start writing what I would recommend. Maybe I would like work through this how if this was my homework question. Okay. So question number 3, a street light is mounted at the top of a 15-foot pole. A man, 6 feet tall, walks away from the pole, the speed of 7 feet per second, along a straight path. How fast, in feet per second, is the tip of his shadow moving when he is 35 feet from the pole? Ooh, okay. So just want to kind of break down everything that they give us here because it's a lot, you know? Okay, so first of all, we have a lovely street light. I usually start by like trying to get an idea of what this looks like. Okay. It's not going to be pretty at all, but it'll be something, it'll it'll get the job done. So there is a street light again. And let me go ahead and try to fix this a little bit. I have to have at least my street light a little bit straighter than what it is right now, which looks to be more challenging than one might think. Okay, here we go. Okay, I hope you enjoy my lovely drawing here. Okay, so we have a street light on top of a 15-foot pole. We have a 6-foot man who is walking away from the pole. That's going to be like my husband tonight walking away from the trick-or-treaters because it's Halloween today when I'm recording this video. Okay, so then that's what they give us essentially. Again, they do tell us that this man is moving. He's moving. He's got places to go. He's moving in the positive direction at 7 feet per second. Again, I'm just sort of getting everything down, and then I'm going to come back and see if I can try to make sense of it all. Okay. And then they want to know like how fast is the tip of his shadow moving, which I mean, I guess, so this street light is shining down on this gentleman, and somewhere there's got to be a shadow, right? And so they want to know like how fast the tip of this shadow is moving when he is 35 feet from the pole. Okay, so just want to make sure they give us some things that are like staying. They could be moving, but they're always there. Okay, and then there's stuff that's just like at a specific point in time. So that's sort of like I usually like to first think about like, okay, what's everything they give us? What's changing? What's not changing? And if it is changing, like when do they tell us like the value is, right? Okay, so like for instance, like we know again, this street pole not changing. Height of this street pole, right? This height is 15. And this man, unless something crazy happens, he's not shrinking or growing. Okay, he's just going to be 6 feet tall. So those are pretty much constants. Those are going to stay the same. They also say, I think we're just going to assume he is moving always 7 feet per second. Okay, straight across there. All right. And then again, they want to know how fast is the tip of his shadow moving when he's 35 feet from the pole. The problem is, okay, like they're telling us that he's moving away from the pole, right? At like 7 feet per second. Like that would be the rate of change of whatever we want to call this value, right? Would be like 7 feet per second, the distance between the pole and him. But like we need to know essentially the tip of his shadow from the pole. We would need to know like the change of the whole shebang, right? And so you can kind of picture like if he's walking, if he's pretty far away, right? I think let's think about how his shadow, like the angle is going to be changing on his shadow, right? And like the farther he moves away, that's going to affect how far his shadow is. And like the shadow is going to get longer, right? Depending on how it's like hitting how the light is hitting him, right? So that's a lot going on there, and we have to try to figure out how to make sense of it. Okay, so first things first, let me see if I can rewrite this lovely situation as more of like a nicer triangle, okay? Because that's what this is. This is just a triangle. So for each of these, again, there's always going to be some sort of key piece of information that we're going to need to use to answer the question. Okay, so they do tell us, for instance, that I know I'm just going to label like in my triangle without all of my lovely pictures of things and people is that the height of the pole is 15. The height of this man is 6, right? We don't know how far this angle is. We don't know how far his shadow is out from what they gave us. I'm going to go ahead and say that the distance between the light and this man is X because they told us again that he's moving away from the light at like 7 feet per second, right? So I'm just going to call it X. You can call it whatever you want. And then I also am probably going to need some sort of letter for the distance from the man to his shadow, which is changing, right? It depends on, again, like if he was really close to this lovely lamp post, right? The way that the light would be shining down on him, right? His shadow would definitely be shorter as compared to like this distance is going to be more spread out. Like the farther he gets away, right? Like the longer the shadow grows, it happens again to be Halloween, right? So, yeah, okay, I think I'm losing it, but I don't know. You could call it any letter you want. I'll call it Y, but you could call it anything. You could say like D was maybe the distance from the lamppost to like D1 is the distance from the lamppost to the man, and D2 is the distance from the man to the tip of his shadow. I just chose to use X and Y. It doesn't really matter, okay? But I feel good about X and I feel good about Y. Okay, so what we're really actually being asked to find would probably be like if it's written this way, would be like the derivative of how it wouldn't be just y, it wouldn't be just dy dt because that would just take into account the distance from the man to the shadow to like the end of his shadow. We want from the light post to the end. So I'm gonna go ahead and say like this would be the rate of change of like dx and of ny. Do you know what I'm saying? That's what I would need to find. That's what that distance would be like x plus y, and I need to find out how that's changing. Okay, so back to the drawing board. I don't even know how I would come up with an equation right now for y at all, you know, let alone x plus y. So what do? So whenever we have this related rates problem, I'm going to go ahead and move out of the WebAssign page because there's a lot going on here, right? Whenever we have these related rates problems, again, I read them a couple times. I usually try to get my bearing straight on like, what are they even describing? And then like the key component is like, what equation can possibly relate all of these things together? Okay. What equation or formula could we use? I don't know. Let's think. Is there any equation I could use that could possibly relate 15, 6, x, and y together? You know, I don't know. Now, there's a whole bunch of geometry formulas you could pull back to, right? Like, I don't know, like how weird do you want to make this? Do you want to try to, like, you probably could even solve this using some sort of like trig knowledge. But if we're even thinking like sometimes the simplest method is the best, like what you learned first. So before you even had to worry about trig knowledge, we learned about similar triangles, right? These two triangles are similar because they have a good 90-degree angle, right? This 90-degree angle is the key component here, okay? And then these two angles would, see, you know what I'm saying? Like those would be the same. Okay, so using similar triangles, we could say it a couple different ways. You could say 15 over 6. So like this is like the longer side in proportion to like the shorter side would be equal to, and then say like longer side would be like x plus y and shorter side would just be y, right? Does that make sense? There's also like other varieties of ways to set this up. You could say instead maybe this total distance was just like y, and then this inner piece was x, right? And you could try to instead set this up as like y take away x would give you like the smaller piece, right? Like you could do that in case that was something you were thinking. Like you don't have to necessarily set it up as x plus y. It's just the way that I chose to do this. And again, there's a couple different ways to do it. If you're not sure if your way works, you can let me know. I can help you. Okay, so the whole reason I'm going to do this is because, again, I'm trying to find the derivative of x plus y. And usually probably the easiest way to maybe do this is just to like get x in terms of y or y in terms of x, right? You know, like any of those will do here. But also we do have that dx, the derivative of x with respect to t is 7. So I feel like it's going to make sense if we use this lovely equation that ties everything together, right? If I could essentially like solve for y in terms of x, right? And then I could use that to then plug it into what I'm trying to find, and then I already have like the derivative with respect to x in terms of time. Does that make sense? Okay, well, let's just go ahead and get started. So we'll say, again, the reason it's so complicated is because there's just, it's triangles, you know, and I feel like, I don't know if anyone really loves those. So first things first, I'm going to go ahead and clear the fractions by like essentially cross multiplying. Okay, so I'm going to say 15y equals 6x plus 6y. And then I'm going to go ahead and get my y's together. I'll say 9y equals 6x. So x equals, if I divide by 9, 2/3 x. Okay, so now I can take that and I can go ahead and evaluate the derivative, oops, with of x plus, instead of y, I'm going to put 2/3 x. Okay, so this would be essentially the derivative of, that's like, what's 1 plus 2/3? It kind of does hurt. I guess it'd be like 1 and 2/3, but I think that'd be like 5/3 x. Okay, is what I'm essentially trying to find the derivative of. Okay, and then what would that be? Well, let's see. The derivative of 5/3 x is just 5/3 times the derivative of x with respect to time. Does that kind of make sense? Because again, that's for all of these, we have to take the derivative with respect to time. And we have that. We know the derivative of x with respect to time. It's 7. Okay, so we say 5/3 times 7 equals 35/3. And then this would be like feet per second. Okay, so this one was, again, I feel like a extra tricky one because there's a lot going on. We really would have to find the derivative of x with respect to time and add it to the derivative of y with respect to time. And the easiest way to do that was to figure out, to solve for y in terms of x using that lovely formula. But again, each of these is a little bit different. And you please let me know however I can help to try these out and to check the answer key and all that good stuff. So again, I hope it was somewhat helpful. Keep me posted, please. These follow like all different trains of thought, so it's hard to really kind of give one overall synopsis. But do please check those steps that our textbook recommends of how to approach these problems. that is sort of like an algorithm that can at least get you started on most of these. The other key part is there's always going to be some sort of formula that relates all of these together. Okay. And so in this case, it was like using the knowledge of similar triangles. If it's like volumes, it's probably the equation for volume. If it's involving areas, it's probably the equation for areas, right? So lots of different things here, but keep me posted. I'm here to help. And let me know how things are going. Okay.